Okay, get on with this afternoon's program then. Kick it off here, the second half here of speakers. We'll do a little discussion on saving energy with proper ventilation, obviously kind of geared more towards how we manage ventilation here and during the wintertime and during the colder months, and how we can minimize our inputs as far as obviously from an electrical standpoint, but also propane usage and so forth. So I would say unseasonably warm for this week, but maybe some of these principles, could have been certainly ones you guys encountered or dealt with there about 14 days ago or 2 weeks ago and so forth when we were highs in single digits. So we'll talk a little bit about on this. Again, know many folks here in the room, but Matt Romoser, swine field specialist here for Iowa State, covers Southeast Iowa. My background's actually a little bit more in physiology. So when I think about this, I'm looking at more from a heat stress standpoint and the effects that has on the animal, less on the engineering and the science behind the ventilation system. That's where Brett Ramirez comes in with Iowa Pork Industry Center. He would have put this slide deck together. So certainly I'll do my best to answer any questions you guys have, but also have Brett's contact info listed here at the end of this presentation if you don't have any questions or anything you want to reach out to him about. So, okay, so talking about benchmarking energy, obviously we try to figure out, okay, we're going to minimize costs. First, we have to know what it costs to operate our barn, and if what we're putting in and managing from that standpoint, what we're putting in, and then how much should we be putting into it from a cost standpoint. So obviously there's sort of limited data and limited control studies where this has been looked at, but there is a few examples here we'll talk about. This is actually one that would have been done by University of Minnesota. So at least representative of Midwest environment, maybe representative barns that are going to be a little bit more, seasonably colder compared to where we would be here in Southern Iowa, and also maybe ones that would endure a little bit longer winter time as well. But nonetheless, at least gives you some of a background story on how we can benchmark energy. So we got two different style barns here, what we'll call finishing barn A and finishing barn B, two different types of barns where we've got one that's a 2,400 head site, 2-room, and the other one is a 2-room, 530 head, so roughly 1060. And I think just the important thing to point out here is just the difference here in ventilation type and the cost associated with it. So we've got finishing barn A, it states here, a power ventilated barn, tunnel ventilation system, compared to a naturally ventilated barn with stir fans there in finishing barn B. So I've got it highlighted there at the top, and obviously, I'm sure as you guys would all expect, the cost as far as kilowatt per market hog is going to be higher for a power ventilated barn. So in this instance, roughly 3.5 times more kilowatt hours per market hog in this example, right? Now, again, you're dealing with one barn that's twice the capacity, and still we've got the total kilowatt hours per year listed there at the bottom. So looking at finishing barn A at 91,000 kilowatt hours versus a barn that's half the size and naturally ventilated at roughly 1,100 kilowatt hours. So obviously, more or less, just moral there is just the difference in what you're going to have based on ventilation type as far as energy usage. But then also important to point out just the propane usage there as well. So obviously, we've got a pretty dramatic difference in kilowatt hours based on ventilation system, but only about 70% reduction in propane usage when we're looking at that power ventilated barn versus a curtain sided naturally ventilated barn. And we'll talk a little bit as to why that is. Obviously, still a reduction there in this instance with a power ventilated tunnel barn comparatively, but we'll talk about obviously the costs associated with optimizing minimum ventilation there. Again, another study here showing this one was done about roughly 10 years ago, looking at 30 different farms and obviously different types of farms as well, but at least getting a little bit more representative sample here across Iowa, Minnesota, and Missouri. So in general, a good summation of this is the literature is going to say roughly around 11 kilowatt hours per market hog is a good benchmark to start with, and that's per market hog, okay? And then propane is going to range, obviously, again, as we see here, where we've got sites ranging from Minnesota to Missouri, and something that's going to change dramatically depending on the year, where I would say this, in general, this year, winter's been unseasonably warm or uncharacteristically warmer than average, right? But in general, on average, from this particular study showed about 0.28 gallons of propane per market hog here. So I think in order there's lots of numbers on this chart, so it's easiest just to be able to highlight and draw attention to kind of what a good goal is. And these are by no means, an exact number. Truthfully, depending on the year, you don't really know how attainable some of these are going to be as well. But when we're looking at grow finish barns and wean to finish barns shown here, at least from an electrical standpoint. You're looking at, a good benchmark saying roughly 25 kilowatt hours per space. And then the goal for propane usage here, obviously going to be very different wean to finish versus grow finish, and the requirement for that younger pig to be able to get started. So depending on what your site's going to be set up as, obviously maybe trying to keep it limited to half gallon per pig space per year, or in wean to finish probably closer to around 3 gallons. Obviously, sow farms, I don't know if there's any folks in here with sow farms. Obviously, there's going to be substantially higher with the demand that it takes for all the zone heating required in farrowing, right? So it can be easy. I think in general, sometimes ventilation can be made rather complicated, right? Or thought to be rather complicated, but there's lots of different things that we can do from this standpoint as far as troubleshooting. We like to think that as far as a lot of the complex principles we want to talk about with ventilation, whether it's CFMs and properly sizing our fans and all this sort of stuff. There's lots of different little maintenance things that we can do every day that can really help optimize the performance of that ventilation system. And obviously, if things aren't working properly, you're never going to be able to get optimization really determined within that barn, right? So we see plenty of examples here where we've got dirty shutters or broken shutters, curtain there that's maybe not fully in the pocket, maybe creating draft that way. I think we can all see, I think the pit fan there looks like somebody took their boot right through the side of it, perhaps. Dirty soffits, busted cones off of fans, all different things obviously are going to lag or drag on the performance overall of that ventilation system. So obviously you don't want to be able to do, obviously we want to be able to manage everything inside the barn as possible, but don't make your job more difficult than what it is necessarily per se. If we can do all the little things right and not sort of have death by 1,000 cuts, right? Just keeping those little things in check. So basics of ventilation, this is a 1,000-foot view, obviously, but we want to draw fresh air in, mix it effectively within the air within the barn, and then we want to exhaust the stale air out, okay? And what we're trying to mix, obviously, is the temperature within the barn. We want to make sure if we're bringing cold air in, we're effectively mixing with the warm air that's already in the barn, as well as mixing it with dust and pathogens. Anything that we can exhaust out of the barn to make the air quality more favorable for those pigs is going to be important. And then obviously in certain times of the year, exhausting gases and moisture is going to be our priority. So why do we ventilate? Again, kind of continue with a broad overview of this, but we get outside temperatures that exceed sort of our balanced temperature of what we want. Obviously, we're ventilating for removing heat from the barn, whether that's just normal increase in temperature from outside or the latent heat that pigs are going to be producing, whether it's through respiration or the general heat that they're producing, just being, having a high volume of very active pigs in the barn is just going to be able to generate heat themselves. And obviously we want to be able to create, in some instances, maybe a wind chill effect to be able to draw air over those pigs to keep them cool. Get below that, we start to become more controlled about moisture control and gases within the barn. So just trying to keep that at a minimum ventilation rate, and then keeping relative humidity and any sort of gases at a minimum, while still keeping the temperature comfortable for those pigs in the barn. So this is where it kind of comes in from an energy efficiency standpoint, air quality. Obviously, we can underventilate the barn and really reduce our costs and propane usage. But what's that going to do from the air quality standpoint from the pigs, from a dust, from a humidity standpoint? It's going to create a more favorable environment from pathogens, and obviously can lead to reduced performance or a nagging cough or potentially in the barn. So obviously we want to be able to make sure we're providing a healthy environment for the pigs, but reducing our costs and inputs from an LP and electricity standpoint. So obviously ventilation can consume less energy than heating and cooling. However, there's a certain amount of outdoor effects that can challenge the heat and cooling loads that we have to be able to combat with as well, right? So really, I guess the takeaway from this graph is trying to find that black dot, I guess, in that graph, trying to find that optimal zone where we're kind of right above where, right below where that target pollutant level is, trying to keep those air quality pollutants at a minimum, but still minimizing our amount of input that we're putting in from an energy standpoint. So where does all the heat go? Thinking about from when we're obviously ventilating and managing a barn here in the wintertime. This is all theoretical values that we would say, but if we've got 30-degree temperature difference here from inside a barn to the outside of the barn, so I would say fairly standard of what we've experienced overnights this week, right? Where maybe we're trying to keep our barn in the 60s, but we're getting overnight lows in mid to low 30s, right? So very realistic example here. Sidewalls, curtains versus solid. No surprise, you're going to have a lot more heat loss, a lot more BTU loss through a curtain than you would a solid wall, just simply because there's not as much insulative capacity, right? Stem wall 6 inches thick around the outside, insulated versus uninsulated. No surprise, we're gonna have more heat loss through the uninsulated one. Same for ceilings. Obviously, looking at just different levels of the amount of fiberglass insulation blown in through the ceiling. What's that going to do from a heat retention standpoint? Holes in the curtains. Anyone have those? Nobody. Great. Obviously, it goes without saying heat loss through there, but also just the challenge that comes with properly drawing air into your attic and being able to control where that air is infiltrating from is the bigger problem with obviously holes in curtains and so forth. But highlighted at the bottom, obviously the biggest loss of where that heat is going to go right out through the fan. All as a part of trying to maintain that relative humidity level, the moisture in the barn, as well as just trying to keep the gases at a minimum, right? So in this case, theoretical calculation at 1,200 head at 2 CFM, 79,000 BTU. I think a gallon of propane is like 90,000 BTU or 92,000 BTU, somewhere around there. So in this case, a gallon of propane an hour, it's 2 CFM per head. Again, theoretical calculation shown here. It's the impact of changing indoor temperature. So figure there on the left. Obviously, we look at across the bottom there, we're looking at room temperature. We've got our wide range there showing of different set points where we're looking at roughly 72 degrees Fahrenheit up to 90 degrees Fahrenheit. So pretty wide range, roughly 18 degrees. And just looking at the difference that temperature or the room temperature can have on propane usage. So if we're looking at 72 degrees Fahrenheit, that's probably, again, this is a theoretical model here of what we would expect. Looking at 1.5 CFM, we're roughly probably around that 2.2 and maybe up to 2.7 there when we get up to the set point of 90, right? Well, if we're looking at 2 CFM per head, we're already starting at 2.9, right? And then graduating up to about 3.5. So basically just the iteration there is just to show that CFMs and the amount of heat you exhaust out the barn has a bigger impact than even what variation in this case on a modeled scenario, what 18 degrees difference in barn temperature can make, right? So it's that ventilation and exhausting a lot of that warm air out is what has a lot more bigger impact on that propane usage. So a different way of thinking about this and looking at it then is with the figure on the right. So if we use 2 CFM as sort of our standard and just looking at a room that's the temperature at 79 degrees Fahrenheit, and we change it up and down, 6 degrees or 4 degrees, what's that effect does that have on propane usage? You can see that the 2 CFM per head, which is sort of the, intermediate blue, really doesn't have that much of an impact, probably less than 10% change in propane usage across all those different temperature gradients, right? It's really once you start to get to the 1.5 CFM or 2.5 CFM, you start to see the bigger extremes off either end of that, where we're looking at the impact on propane usage. Again, a lot of the similar information here, but just looking at the temperature difference inside to outside. So maybe looking at 70 degrees difference would have been what we would have had maybe 10 days ago. And obviously the difference we can have there from 1 CFM per pig up to 4 CFM per head. Again, just illustrating the fact that it's a lot of that air movement can result in a lot of bot air, if you will, going out through the fans. So what's the difference between obviously how we design our barn in operation and how do we calculate that minimum ventilation exactly? Obviously how we're going to design it is going to be challenging because we're going to have to design it obviously for different extremes at different times of the year. So we need to be able to figure out, okay, what's the maximum ventilation we're going to need in the hottest days of the summer, and then what's the minimum ventilation we'll need during the winter time. So easiest way from just a simple design standpoint is to keep it fairly simple, just from a diameter of the fan times the number of fans you'll need to be able to get that design that minimum ventilation. And then obviously from an operation standpoint, you're going to utilize the sensors, not only the ones, the electronic ones you put in the barn, but also letting those pigs, do a lot of the detecting for you as far as reading their behavior and what their comfort level is in the barn, right? Whether looking through there and do the pigs, are they piling? Are they spread out? Do they feel, is there a dampness in the room? What's it smell like? Things like that. So lots of different things you can do to obviously from an operation standpoint. Space heater control and understanding the differential and offset. Obviously a big piece that we're going to try to keep track of or monitor so we're not wasting a lot of that heat energy to go out through the fans. So obviously we've got a heater on off, and the difference there in this, at least on this figure shown here at 1 degree, what we would term the differential. And then the offset is going to be from that off time to the set point. So the set point is what we're going to obviously put in as our target temperature. And we want to be able to make sure that offset is enough so where we don't have a lot of that fresh heated air being put in there and then immediately being exhausted out the barn, right? So the challenge that can come then is obviously if we have that offset too tight. In this case, we'll show an example at 0.5 degrees. So previous slide of 1.5, this one's at 0.5 degree Fahrenheit. We can overshoot that set point. So the fan will turn on, and then obviously once that turns off, the barn and the heat that furnace has put out has to be mixed effectively into the environment. So in theory, the barn temperature is going to continue to rise. So we've just put a bunch of hot air into the building, and then the fan's going to take that out once it gets above that set point, because then it goes into cooling mode, and it wants to be able to bring the barn temperature back down, right? So we want to make sure we don't have that too tight to where we're really ultimately putting a lot of extra hot air or heated air out through the fans. So this is a good example here to show kind of what the difference is and as far as fine tuning that heater offset. So some recommended heater settings, the ones that shown there on the left are good ones to start with. The ones here in the graph are a little bit, vary just a little bit, but it's kind of an interesting figure to show. So to set it up, we've got outside conditions. It's a little bit tricky to see there at the top of that slide, but outside conditions, in this case, steady temperature at 34 degrees. So imagine it's probably an average of a 24-hour period. And the only difference here between the left side and the right side is the offset from the furnace off to the set point. It was 1 degree on the left and 1.5 degrees on the right. So you can see we get sort of a yo-yo and a roller coaster with that furnace turning on and then exhausting air in. It brings the barn temperature down. Furnace kicks back on. So the amount of the minutes per hour that furnace was running, obviously you can see is much more sporadic. And then at noon, in this particular case, they adjusted the controller set point from 1 to 1.5. And at that point, you can see the barn really held its temperature fairly constant for the remainder of that 24-hour period. And there was no ramping up of the pit fans, which is what we want to be able to minimize, right? We don't want that furnace kicking on and then the pit fans just pulling that air straight out of the barn. So obviously in this case, I think from this particular study, if I remember right, reading back at it, I think it was like 3.7 gallons per hour. Propane is what it would have been burning given the left side of the graph versus I think maybe 0.5 gallon per hour on the right side. So just important to be able to make sure we're managing that offset. And certainly as soon as the furnace turns off, listening to make sure that variable speed pit fan doesn't ramp up and exhaust more of that air out. We want to be able to maintain that minimum ventilation through that barn. So talking about variable speed fans, then common questions associated with them. What minimum speed do I use? Does the percent reading on my controller mean percent capacity of the fan? What does my system have, or why does my system behave differently after I've replaced a fan motor? So all different things that may come across. In general, what does 50 mean on my controller? So Brett Ramirez kind of highlights this. Does it mean 50% CFM, RPM, or the rotations for that fan, 50% voltage, 50% of some random number, which according to Brett would be true just because all controllers are going to be a little bit different on what that 50 is going to mean, right? In general, for variable speed fans, important to point out that 50% speed does not necessarily equal 50% CFM. And we'll show a graph here that kind of demonstrates that. 50% voltage does not equal the CFM per RPM. Obviously, every motor is going to react to voltages differently, so we'll show some slides that kind of help illustrate that. And then minimum speed should never really fall below 50% RPM. Thought being there that if there's any sort of static pressure that fan has to pull against, it's going to be it's going to be a lot less effective at 50%, or if it's got any sort of direct wind, going back up against it, it's going to really impede the effectiveness of a fan at 50%. And then for sake of this conversation, and I would say Brett would probably echo this, that most fans or almost every controller controls variable speed fans by changing voltage. And I think Brett would be aware of fans that operate a little bit differently, but for the most part, all going to be controlled by changing voltages. So how does your controller work with variable speed fans? So important to point out in just discussion about how we describe the relationship between the voltage that's supplied to the motor and then how it ultimately turns that into RPM. So that's what we're going to call or that's what's going to be classified as the motor curve. So varies in this motor. It varies within motor make and model and size of those fans. So different motor curves obviously going to exist for different sizes of fans and motors there. And it's important to just be able to select the right curve for the controller to make the ventilation rate increase as smoothly as possible as you're transitioning through, obviously with warmer temperatures and throughout the day, to make sure that's a smooth transition from as we increase airflow through the barn, right? So you can see obviously in that graph there, as we've got controller variable speed settings, we can see that what would be ideal shown by the linear blue line, and obviously the percentage of that actual airflow that's measured is going to follow that trend line, but it's going to vary a little bit. So obviously it's not a perfect science here, but we try to do it as close as we can by controlling those motor curves. And so when we think about the amount of voltage or the 50% voltage that's supplied to a fan in simple terms, we'd think it would be 50% CFM, but showing here, we can demonstrate it's not the case necessarily, where we've got this is one fan graphed at 7 different voltages, right? So at 230 volts, the top line there at the red, if we're looking at, say, a winter time where we've got maybe a static pressure in the barn of, say, 0.1. Obviously, at full power, we can move roughly 7,000 CFM, at least in this case. But if we go to even half voltage, or 120 in this case, moving substantially less CFMs, roughly around 800 or 900 in this case. So again, it's not 1-to-1, not 50% power equates, again, obviously to 50% CFM through that barn. So for example, here with APP 24-inch fan, just looking at how that voltage supplied can change and ramp up as we look at that motor curve. So we can see just the voltage supplied there from 230 to 194, 46 volt difference, only a change in this instance in the motor speed of 100 RPM, right? But as you can see, as you work down through those different voltages supplied there, obviously as it decreases, we get a fairly uniform and linear decline in motor speed from there at around 100 RPMs with each reduction at a different stage there. So again, this would be ideal, obviously, what we want our motor curves to look like. And this is a better, more representation of how linear that should be when you look at it from the RPM ramp up stage as far as the CFMs, obviously following closely to that as well. So then talking about obviously understanding the motor curves, again, that's just the voltage that's supplied to the fan and how it turns it into RPMs, right? So if we're looking at motor curve 4 versus 8, in this case, and we have them both set to 90, say an example, if we had, obviously have them set to the right motor curve. So I'll use the one that's highlighted there at motor curve 8. If that motor is set to actually operate on a 4, and it's only getting 128 volts, wherein ideally it would be getting 186 volts, probably not getting the RPMs and the airflow through that barn that would be necessarily what you would be desiring. So at that point, either resizing the fan motor or trying to do something to obviously increase air movement and airflow through that barn would be important to do. And then again, just making sure the motor curves match are that much more important. So you can see in this case where we've got a 12-inch fan versus say the extreme at a 24-inch fan at different voltages. Obviously, at 1 voltage, you can get one fan that's obviously not working near as hard as say even at 132 volts. That 12-inch fan is effectively function at 90% capacity at that point. Okay, so we go to the outside of the barn then, and other things we can do to obviously manage effectiveness and efficiency of that ventilation system is obviously making sure those soffits are clean. Even bird netting can collect dust and corn fines. Obviously during the fall where lots of dust is in the air, right? So keeping those free of debris, whether it be with a leaf blower or something, to be able to keep dust off of them, and also important to check any sort of insulation stops at that point. The importance of tightly sealed housing. So a few examples here of what we can look for. So I think the picture on the left, the green, it's a little bit tough to see, but I believe somebody took spray foam insulation, just sealed off a door. So obviously that door is now out of commission, but just trying to way to seal up cracks. Obviously the picture it's not illuminated with a thermal camera is just the obviously pictures of fans being unused in the wintertime. So finding ways to seal those up. And you can see kind of in this picture here, that's what this is showing. It's just getting some of a plastic cover over a non-used fan during the wintertime can dramatically decrease the leaks and gaps of cold air entering the barn. And obviously making sure your inlets are sealed up well. When we look at it from the left versus the right one obviously is getting that cold air and sending it out and away, and it helping with that mixing into the environment versus the one there on the left where you've kind of got air seeping in from all sides of that inlet there. So these are views from within a poultry barn here, but still shows a good representation of what good air circulation and combining that outside air in can look like when we look at it through a thermal camera. So obviously that's what the top one represents, a very relatively uniform environment from a temperature standpoint, where you can see in the bottom left, we've got that cold air coming in immediately dropping, or in the bottom right picture, we've got that air that comes in through the inlet, goes across the roof, and then hits some sort of an object and drops straight down, ultimately leading to really warm, stale air staying in the middle of that barn there, in the middle of that house. So again, just some things to kind of touch on, just as common causes of increased energy costs. So gas line leaks we'll touch on just a little bit. Obviously, we've already talked about variable speed fans. I would say if Brett were here, he would probably tell you 2 things that you could really do to help minimize your costs is keep your house or keep the barn really tightly sealed and minimize cold air infiltration into the barn, as well as making sure that offsetting for that furnace is the offset is tuned in properly, so we're not sending a lot of expensive heated air out through the fans. Winterization, obviously, putting in some sort of a bubble wrap along curtains can certainly be a benefit. It doesn't necessarily provide a ton of insulative capacity with the bubble wrap, but what it can do is create sort of an air gap between it and the curtain, and then obviously the radiant heat then comes off that bubble wrap is what the pigs feel versus the 30-degree radiant heat coming off the curtain there. So other things to consider, obviously gas leaks, high pressure gas lines, have those inspected. Generally, the propane supplier will do that at no charge. When we think about it from where some of the most susceptible points, probably where that gas line enters the barn, where it's subject to a little bit more weather and wider temperature swings comparatively. And then obviously having a furnace appropriately sized for the barn there as well. Talk about heater location then. I'm sure most folks in the room probably familiar with this, so won't touch on it too much, but obviously it doesn't make a whole lot of sense for that fan or for that furnace to be blowing air in the direction in which those fans are going to pull it, right? We want to be able to get that warm air to be able to effectively mix in the environment to avoid any sort of cold spots within the barn. So in this case, we got our correct location shown in the top and a wrong location shown in the bottom, where effectively those furnaces are pointed in the same direction or towards where the fans are, the exhaust fans are for the barn. So simple analysis and solutions for common problems. If the room's too cold, obviously we can check and adjust temperature settings, ensure the temperature sensors are located properly. We want those to be located where they're obviously representative of what the pig is going to be feeling and experiencing in that environment. But also, you know, we don't want it so low to the ground where it's really not representative of the of where that air can be mixed within the environment as well. Seal uncontrolled infiltration. So again, just closing up any holes, and you'll see a theme here as we go through this. Cold drafts, adjusting the air inlet openings, seal exterior infiltration sources, and then potentially looking at second stage fan if we've got too many drafts coming through. Excessive relative humidity, obviously looking at increasing your minimum ventilation, checking insulation around the ceiling, and things of that nature. If there's excessive condensation around the air inlets, maybe we need to look at how we're mixing that air in through the room. And then if it's near the exhaust fans, you know, putting some sort of a cover around the fan to help seal those perimeters then. Gases and odors, again, typically improving air distribution. So trying to make sure that we're getting that air effectively mixed. And then if we've got low static pressure, and again, ensuring we're controlling where that air is entering the barn. We don't necessarily want it entering, you know, half of our air coming in through inlets and the other half coming in through holes in the curtains, right? Because we're not getting as effective a mix with that air entering the barn. Done. Perfect. Well, if you do have any questions, I would encourage you to reach out. I left Brett's contact information on this. Obviously, he's the one within the Pork Center team that specializes in this. So I've got left for him if you want to take a picture of his email there. So.